In the last video, we derived an expression for how the stagnation pressure decreases as a flow passes through a normal shock wave. I now want to move on to link the loss in stagnation pressure with the increase in entropy of the flow that occurs as it's processed by a normal shock wave. This should really bring out the point that we can't apply the isentropic flow relations across shock waves. Let's do this through a thought experiment. Consider a pressure vessel containing gas at high pressure that has a convergent-divergent nozzle attached to it. Let's say that the gas in the vessel is at condition 1'. We'll assume that the vessel is large and the throat of the nozzle is small. So the speed of any flow near the middle of the vessel will be approximately 0, and we can consider state 1' to be the stagnation condition. Now let's consider what happens to the flow as it moves from state 1' along a line right down the middle of the nozzle to its exit. This is a converging diverging nozzle. So if the pressure inside the vessel is sufficiently high, we'll get a supersonic flow downstream of the throat of the nozzle. As we move along the nozzle downstream of the throat, the Mach number will increase because we have an increasing area and it's a supersonic flow. Let's now say that there's a normal shock wave that forms across the nozzle. And we'll say that the gas is at state 1 upstream of the shock wave and state 2 downstream of the shock. Now let's assume that the flow from state 1' to state 1 is an isentropic process. That's reasonable if viscous effects are neglected. We just have the flow starting from rest, expanding to sonic conditions at the throat of the nozzle, and then expanding supersonically up to state 1. Now, since the flow speed is 0 at state 1', and it's an isentropic flow from 1' to 1, then the pressure inside the vessel is going to be the stagnation pressure for state 1. We denote that as P01. Now let's look at the flow on the other side of the shock wave. Since it's a normal shock wave, we know that the Mach number for state 2 must be subsonic, less than 1. Remember that the Mach number downstream of a normal shock wave is always subsonic. Imagine there's a body in that subsonic flow, and let's allow the flow to stagnate at the nose of the body. We'll number this as state 2'. Let's now assume that the flow from immediately downstream of the shock to the stagnation point on this body is isentropic. So the pressure at the nose of this body will be the stagnation pressure for the gas at state 2. So the pressure on the nose is P02. Let me summarise that. We have a high pressure gas in a reservoir. We let that gas expand isentropically through a convergent divergent nozzle, giving us a supersonic flow in the nozzle. We then have a normal shock wave in the supersonic flow in the nozzle, taking us from supersonic to subsonic conditions. Then we bring the gas to rest at the nose of our object through another isentropic process. So, everything from state 1' to state 2' occurs through an isentropic process except for the flow through the shock wave. Therefore, if we look at what happens to the entropy of the flow from state 1' to state 2', then any change must be due to the entropy change across the shock. So we want to consider the flow as it goes from rest at state 1' through the nozzle and shock and comes out to rest at state 2'. I'm going to pull up a result from thermodynamics here. From thermodynamics, we can write the change in entropy of a gas as it goes from one state to another in this form. The entropy change, delta S, depends on how the static temperature changes through this process and how the static pressure changes. Let me move on to the next page and make the sketch a little smaller. Look at the first term, T2' over T1 prime. Now both of these states, 2 prime and 1 prime, are stagnation states. And we know that across shock waves, the stagnation temperature doesn't change under our calorically perfect gas assumptions. Therefore, T2 prime is equal to T1 prime, which equals the stagnation temperature T0. Therefore, T2 prime over T1 prime is equal to 1. The natural logarithm of 1 is 0. Therefore, the first term is 0 and it drops out. So we are left with just this as the change in the entropy for our process. Let's look at the term P2 prime over P1 prime. Again, since both state 2 prime and 1 prime are stagnation conditions, we can say that P2 prime is equal to P02 and that P1 prime is equal to P01. When we put this into our expression for the change in entropy from state 1 prime to state 2 prime, we get that the entropy change is equal to minus R log P02 over P01. Now let's look at that. We said that for a normal shock wave, the stagnation pressure always decreases across the shock. Therefore, P02 over P01 is always less than 1. The log of a number less than 1 is a negative number. So log P02 over P01 will be negative, and delta S has to be positive across a shock wave. Therefore, entropy always increases across shock waves. So the ability we'll have to extract work from a gas decreases when it's been processed by a shock wave. And the stronger the shock wave, the larger is the stagnation pressure drop and the higher is the increase in entropy. And we've lost more of that opportunity to extract work from the gas. The implication for our scramjet design is that we'll want to minimise the strength of any shock waves that occur through the engine. This is not yet the full story. We've only considered normal shock waves. Next we'll see what happens when shock waves are not normal but are inclined at an angle to the oncoming flow.